Welcome to Data Mining with Python. This lesson is for absolute beginners. You will learn to load, clean, and explore data. We will cover association rules, classification, clustering, and more. We will use Python libraries like Pandas and scikit-learn. Do not worry if something is new. Let us start your journey into data mining. Running the cell now. We will turn off warnings so the output stay clear. This helps focus on the main results. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. Here, we set up our environment by suppressing warnings and fixing the random seed for reproducibility. Although this code produces no visible output, it ensures that our future data operations run smoothly and generate consistent results, laying a clean foundation for learning data mining. Let us begin by loading the iris dataset. First, we import the Pandas library. We download the data from a public GitHub repository. We then load the data into a Pandas data frame. We print the shape to see how many rows and columns are present. Here, we preview the first few rows. This gives us a quick look at the data. Running the cell now. The output shows the dataset has 150 rows and 5 columns, indicating we have 150 flower samples with measurements and species labels. The first 3 rows preview the numerical features like sepal and petal dimensions along with the species name, confirming the data loaded correctly. This helps us understand the structure and content before we begin exploring and cleaning the data. Try running this cell. What do the column names tell you about the type of data we have? What is data cleaning? Data is not always ready to use. It can have missing values or errors. Cleaning means fixing or removing bad parts of data. Running the cell now. Here, we check if there are any missing values in the data set. The code counts the missing entries in each column. Running the cell now. This output shows the number of missing values in each column of the data set. Notice that all columns have 0 missing values, meaning the data is complete and ready for analysis. This confirms that no cleaning is needed for missing values in this dataset, illustrating an important first step in the data cleaning process. If there are missing values, we fill them using forward fill. Forward fill means copying the last valid value forward. After that, we check again to be sure there are no missing values left. Running the cell now. This output shows that there are no missing values remaining in the dataset after applying forward fill to replace them. The code's intent was to clean the data by filling gaps using previous valid entries, ensuring no nulls disrupt analysis. Notice how the count of missing values dropped to 0, confirming the cleaning step was successful. This is a basic way to clean missing values. Try to explain in your own words what forward filler means. Sometimes, the same row appears more than once by mistake. We print the dataset shape before removing duplicates. We remove any duplicate rows so that each row is unique. We print the shape again to confirm the change. Running the cell now. Here, we see the dataset shape before and after removing duplicates, with rows dropping from 150 to 147. This shows that cleaning removed 3 duplicate entries, which helps ensure our data is more accurate and reliable for analysis. Noticing these changes confirms that data cleaning improves quality by eliminating redundant information. Exploratory data analysis. Exploratory data analysis, or EDA, finds patterns, trends, and surprises in data. We use simple stats and plots to understand what data shows before applying models. Running the cell now. Now, we want to learn more about our numeric columns. This will help us spot outliers or unusual values. This gives us the count, mean, minimum, and maximum. It shows us stats for each numeric column. Running the cell now. This summary shows key statistics for each flower measurement, like the average petal length around 3.78 and the range spanning from 1.0 to 6.9. Notice the count confirms we have 147 samples, indicating no missing data here. This quick snapshot helps us understand the data's distribution and scale before moving on to deeper analysis. Next, we will see our data in a plot. We use matplotlib to make a scatter plot with sepal length and petal length. Each dot shows one flower from the dataset. This kind of plot helps us spot relationship patterns. These labels explain which measurement each axis shows. Adding a title helps explain the purpose. Showing the plot lets you explore visually. Running the cell now. This scatter plot shows the relationship between sepal length and petal length in the dataset, revealing a positive trend where longer sepals generally correspond to longer petals. Notice the spread and clustering of points, which help identify potential patterns or outliers before deeper analyses. This visual step is key in EDA to guide further modeling decisions by understanding how features interact. Association rule mining. Association rules uncover items that appear together in data. Stores use these rules to learn which items are bought together. Let us try it using a small version of a groceries dataset. Running the cell now. Let us load the groceries dataset for association rule mining. We import Pandas and KaggleHub. We download the data using KaggleHub, so no need for local files. The path is set to where the dataset is downloaded. We list all files downloaded. We select the CSV file automatically. We load the CSV file into a Pandas data frame. We print the shape to see rows and columns. This is a preview of the first few records. Running the cell now. The dataset contains 38,765 rows and 3 columns, showing transactions by member number, date, and the purchased item's description. Notice how each row represents a single item bought in a specific transaction, which is essential for finding associations between items later. This setup prepares us to analyze which products tend to be purchased together. Create groups of items purchased together by each shopper on each date, called baskets. Group the data by shopper, then collect the item descriptions into lists for each group. Display the first 3 baskets to check the grouped results. Running the cell now. This output shows the first 3 rows of the basket data frame, where each row represents a unique shopper identified by member_number, and the corresponding list of all items they purchased. Notice how the item description column aggregates multiple items into a single list, setting up the data for association rule mining by representing transactions as item baskets. This transformation is essential because association rules analyze patterns of co-occurring items within these group transactions. Convert baskets from lists to a one-hot encoded format to prepare for analysis. Import the transaction encoder class from the melksten.preprocessing module. Create an instance of the transaction encoder to encode the transaction data. Fit the encoder to the item description column and transform it to a one-hot encoded array. Create a data frame from the encoded array with item names as column headers. Print the shape of the one-hot encoded data frame, showing baskets, rows, and items, columns. Running the cell now. This output shows the shape of the one-hot encoded data frame, where 3898 represents the number of baskets, transactions, and 167 represents the unique items across all baskets. Notice how the transaction encoder transformed the list of items into a matrix format, which is essential for running association rule mining algorithms that analyze item co-occurrence patterns. This step sets up the data for discovering which items are frequently bought together. Apriori is a popular algorithm to find groups of items bought together often. We set a minimum support of 0.01, so only items in at least 1% of baskets are kept. The result shows the most common item groups in our data. We print the first few to see which sets are frequent. Running the cell now. This output lists the most frequent single items in the grocery dataset, each with its support value indicating the proportion of transactions containing that item. Notice that beef has the highest support here, meaning it's the most commonly purchased item in this sample. This step helps us identify popular items as a foundation before discovering item pairs or sets that often appear together. Association rules show strong links between items. We used lift to measure how much more often things happen together than by chance. We only show rules with a lift greater than 1.1. This table summarizes shopping patterns in easy numbers. Running the cell now. This output shows the top 5 association rules mined from grocery item sets, sorted by lift, which measures the strength of item co-occurrence beyond chance. Notice the antecedents and consequents are combinations of products frequently bought together, with support indicating how often these appear in transactions, and confidence showing the likelihood of the consequent given the antecedent. These high lift values confirm the rules reveal strong, meaningful associations that stores can use to optimize product placement or promotions. Try changing a minute_support or the minute_threshold to see how rules change. If you are enjoying this, consider subscribing to keep learning. Classification basics. Classification puts data into groups or classes. For example, predicting if a flower is setosa, versicolor, or virginica. Let us train a simple decision tree on the iris data. Running the cell now. We start by preparing the data for classification. We import train_test_split, which helps us split data into training and testing sets. We create X by dropping the species column from the data frame, keeping only features. We create Y by selecting the species column as the target variable. We split the data into training and testing sets using an 80-20 split with a fixed random seed. Running the cell now. This code splits the iris dataset into training and testing sets, preserving the key features in X and the target species in Y. Notice how 20% of the data is set aside for testing, which ensures we can evaluate our decision tree's accuracy fairly on unseen data. This step is crucial for building a reliable classification model. This line is a comment explaining that we will train a simple decision tree classifier. We import the decision tree classifier class from scikit-learn's tree module. Here we create an instance of the decision tree classifier with a fixed random state for reproducibility. We train the decision tree classifier using the training data features and labels. We evaluate the model's accuracy on the test data using the score method. We print the test accuracy, showing how well the model performs on unseen data. Running the cell now. This output shows the test accuracy of our decision tree model on unseen iris data, scoring about 93.3%. This high accuracy indicates the model is effective at classifying flowers into the correct species, which aligns with our goal of learning how classification algorithms group data into meaningful classes. Clustering. Clustering groups data by similarity. Unlike classification, classes are not given in advance. A real-world example is grouping customers by buying habits. Running the cell now. Here, we use the k-means method to group flowers by length features. K-means is a clustering model. It tries to group similar points together. We only use sepal length and petal length for this example. We set the number of clusters to 3. K-means finds these patterns for us. Cluster labels get added for each flower. Each color in the scatter plot is a separate cluster. This is a common first step before doing deeper analysis. This helps you see what kinds of groups exist naturally. Adding a title makes it clear what the plot is about. Finally, showing the plot brings the groups to life. Running the cell now. The scatter plot shows 3 distinct clusters formed by grouping data points using sepal length and petal length from the iris dataset. Notice how the colors separate the points into 3 groups based on their similarity, illustrating how k-means clustering automatically finds natural groupings without pre-labeled classes. This visualization emphasizes the goal of clustering, uncovering hidden patterns in data. Practice, try changing number of clusters. See what happens. Ensemble learning. Ensembles combine several models to improve predictions. Voting and random forests are examples. Ensemble methods are strong in real-world tasks. Running the cell now. Random forest builds many decision trees instead of just one. Each tree learns from a different sample of the data. Combining the results of many trees makes predictions more accurate. Fitting the random forest model is often more stable than a single tree. We print the test accuracy to see how well the ensemble performs. Running the cell now. This output shows the random forest model achieving a high test accuracy of about 93.3%, demonstrating the power of ensemble methods to improve predictive performance. The code fits 100 decision trees and combines their predictions, which helps reduce overfitting and capture complex patterns better than a single model. This reinforces the lesson's point that random forests, as an ensemble method, provide strong and reliable results on real-world tasks. Anomaly detection. Anomaly detection spots data points that are rare or different. This is used to find fraud, errors, or unique behaviors. Let us try a simple one. Running the cell now. Import isolation forest for detecting anomalies in the data. Create an isolation forest instance with a fixed random seed for reproducibility. Fit the isolation forest model to the dataset X and predict outliers. The model labels each sample as normal or outlier, -1 for outliers. Count and print how many anomalies were detected in the data. Running the cell now. This output shows that the isolation forest model detected 44 anomalies in the dataset. Notice how the code labels these rare or different data points as -1, helping us isolate potential fraud, errors, or unique behaviors. This count confirms the model's role in spotting unusual patterns as part of anomaly detection. Introduction to time series data. A time series is data measured over time. Examples include stock prices, temperature changes, and website visits. Running the cell now. Let us make a small time series example. We use numpy to make some random values. We create dates, one for each value. We put these values into a Pandas series with the dates as the index. It looks just like data you might collect each day. Now, we plot the values over time. Markers show each point. The title tells you what this series is. Adding a label explains what the y-axis shows. Showing the plot gives you a look at trends over days. Running the cell now. This plot shows a simple time series with values recorded over 10 consecutive days, indicated by the dates on the x-axis. Notice how each point is connected in order, highlighting how the data changes over time, key for understanding trends or patterns in time series analysis. This visual helps us see the basic structure and continuity inherent in time-indexed data. Mini-project, market basket analysis. You are a store manager. You want to find out which items shoppers buy together. Use association rules to help marketing or optimize layout. Running the cell now. Now, let us focus on pairs. Pairs are rules with one item leading to one other item. Using metric equals confidence, we sort by how likely the second item appears if the first is present. We filter to keep only pairs with a single item as the first part. We sort by confidence, then pick the top 5. Printing these gives insight into true product links. Running the cell now. This output shows the top 5 item pairs with a single antecedent that are frequently bought together, filtered by a confidence threshold of 0.3. Notice that all rules have whole milk as the consequence, indicating it is commonly purchased after these items, with confidence values above 0.58 suggesting strong association. This helps the store manager identify key product pairings to inform marketing strategies or product placement. What business ideas can you think of using these pairs? Write one down as practice. Mini project, classification with Titanic data. Now, let us use the Titanic dataset to predict who survived. Try a simple logistic regression model. Running the cell now. We add a comment indicating the start of the Titanic dataset setup. We import the Pandas library for data manipulation. We define the URL to the Titanic dataset stored on GitHub. We load the dataset into a Pandas data frame called df_Titanic. We print the shape, rows and columns of the data frame. We print the first 3 rows of the data frame to preview the data. Running the cell now. The output shows the Titanic dataset has 891 rows and 12 columns, giving us a manageable size for our logistic regression model. The first 3 rows provide a snapshot of key features like survived, P-class, sex, and age. These will be important predictors in our classification task to determine survival likelihood. This initial data check ensures we understand the dataset structure before building the model. Prepare the Titanic dataset features for modeling. First, we turn the sex column into numbers, 0 for male, 1 for female. We fill in missing ages with the median, so no rows get dropped. We pick only a few columns for simplicity, class, sex, and age. Survived is the label. 1 means survived, 0 means did not. We split the data to learn from part and test with the rest. Running the cell now. This code prepares the Titanic dataset for logistic regression by encoding that sex a column as numeric, filling missing age values with the median, and selecting key features, P-class, sex, age, for modeling. It then splits the data into training and test sets, setting up the structure needed to train and evaluate the classifier. Notice how this pre-processing ensures the model receives clean, numeric input aligned with the intent to accurately predict survival. Logistic regression is a popular method for simple classification tasks. We increase maximum iterations to ensure the model finishes training. Fitting the model learns the connection between our features and survival. Test accuracy tells how well it might do with real, unseen data. A score near 1 is perfect, but do not expect that in real-world work. Running the cell now. The output shows the test accuracy of our logistic regression model trained to predict Titanic survival, achieving about 81% accuracy. This indicates the model is fairly effective at distinguishing survivors from non-survivors based on the features used. This metric reflects the model's initial performance and sets a baseline for further improvements. Best practices and troubleshooting. Always preview and check missing values. Plot your data before applying models. Try more than one model or method. Tune parameters and try again if results look odd. These habits save time and improve accuracy. Running the cell now. Now, pause and reflect. Think about what surprised you most in the examples above. After you type your answer, you will see a friendly note. Running the cell now. This output follows a user prompt designed to encourage reflection on the data exploration process, reinforcing the lesson's emphasis on developing intuition through close examination. Although not a data output itself, it highlights the habit of pausing to consider surprising insights before moving forward, which supports best practices like checking for missing values and validating model assumptions. Extra tips. Use random_state so results can be repeated. Keep code simple and build up step by step. Check what every line prints. Output often helps spot issues. Coding is like learning a new language. It gets easier with practice. Running the cell now. Challenge exercise. Pick a column in the Titanic or Iris dataset. Plot its distribution using matplotlib. Can you spot any patterns? Try one new classifier, for example, k-nearest neighbors, on Iris. Running the cell now. Recap. You learned to load and clean data. You practiced exploring, visualizing, and modeling. You tried association rules, classification, and clustering. You saw how time series and anomalies are handled. You completed 2 mini-projects. Practice is key. Come back and build new projects soon. Running the cell now. Thanks for joining. If you enjoyed this lesson, leave a like or comment and subscribe for more beginner-friendly Python data mining videos. Happy coding! Running the cell now.